Okay, hi. I am going to do Chapter 7, problem number 15, which was the problem that was on the last exam, talking about males and females were basically surveyed to see how often women smiled in a certain time period. So basically, they observed 5 women, and they observed 5 males. Just for clarity, these two numbers don't necessarily have to be the same. I could have done 10 men and compared that to the average of 5 women. It doesn't make a difference. The ends don't have to be the same because that's why they label them N1 and N2. Okay, so just as a refresher, going back, even before we started this, what we did in chapters 1, 2, 3, and 4, and even 5, not so much of 6, but we practiced getting data, collecting different types of central data. And the biggest one is probably the mean, which is what we learned to do. And most of you have done the mean before. You're very familiar with it, just not really the standard deviation. And so I'm going to calculate it the way I know. And then there's another way in the book, and I might try to do that one instead. But for what you have, I've got the 5 guys. And in the 1 hour, basically, let's say it's a 1 hour time frame, this guy smiled 8 times. This guy smiled 11 times. This guy smiled 13. This one smiled 4, and this one smiled 2. All right, so if I get the average of this, if I add up all these numbers just like you would your grades and then divide by 5, I get the average. And so what I find out is that the average, X bar, is equal to 7.6. All right, if I do the same exact thing for women, I'm going to add these up, and I'm going to work out the women's side totally. If I add up all of these, and there's 2 A's, and I think a lot of you just haven't seen them yet. But if I add 15 plus 19 plus 13 plus 11 plus 18, if I sum all those up, I basically get 76. Then I can take 76 and divide it by n, and that'll give me the median. Sorry, the mean. N is 5. Right, so I end up with the mean of the women smiling about 15.2 times. Now, what I would love to say is obviously here, and this is the reason we do the testing, you would love to stop here and go, well, look, the on average, men smiled 7.6 times an hour, women smiled 15.2. Obviously, women smile more than men. But the problem with that is, how do I know that I have a good representation? This is just a sample, and I can't take this sample, because remember, the whole idea of this chapter was you have an entire population, and you're going to pull all these different samples. And what if the sample that I did, these 5 women that I happened to have picked, what if by random, they just all happen to be extra bubbly, extra smiley? And so it's not really fair. I can't necessarily take this scenario or analogy and say, okay, women smile more than men, and therefore all women smile more than men. So what I have to do is I need to test the hypothesis that there's a difference between means. All right, and the way that we do that, because it could be sampling error. What if I just did get a whole group of women who happened to smile? The way to actually test for that is to do what we call a means test. And so we're going to have a null hypothesis. Your null hypothesis is always going to be that there's no difference between the two, that the average number of times men smiles equals the average number that females smiles. And so the way your null will always look is that the X bar of men is equal to the X bar of women. Average smile in men equals the average smile of women. And so your null hypothesis, for the purposes of this class, we're doing a 2-way test, is going to be simply that these two things are not necessarily all the case. And like I said, yes, the data appears that we have evidence that women smile 15.2 times and men smile 7.6, but that is representative of only this sample. I can't make that same claim out for the entire population. So in order to be able to do that, I have to do a means test or a hypothesis test. Now, because I have interval data and because I have two groups, male and female, I'm able to do what we learned in Chapter 7, which is a means test, or differences between means, right? I also need to calculate my standard deviation. I think a couple of you are still having problems with this. The book has one way in the shortcut. I normally do my standard deviation in Excel, where I take 7.6 away from all these. So I've got 8 minus 7.6, and then I square this and so forth and so on. I'm going to try to do it the way that most of you have been doing it, which seems to work for most of you. All right. Let me just make some room here. I'm going to erase this. I'm going to work out the male standard deviation and not the females because I don't have enough room here. But if I take the 8 minus 7.6, 11 minus 7.6, 13 minus 7.6, 4 minus 7.6, and 2 minus 7.6, okay? Let me work these out. 8 minus 7.6 is going to give me 0.4, right? 11 minus 7.6, 3.4. 13 minus 7.6 is equal to 5.4. 4 minus 7.6 is equal to negative 3.6. And 2 minus 7.6 is equal to negative 5.6. Now to do standard deviation, the book stated, and I think in chapter 3, we can't simply just add these up, because if we were to add these up, if I took a negative 0.56 minus a 3.6 plus a 5.4 plus a 3.4 plus 0.4, to know that you're always on the right track, this column here should always sum to 0, because remember the whole fulcrum thing was basically that the median, you know, you have all these x's everywhere, is right in the middle. So if you take the distance between all the x's, they should sum to 0. Does that make sense? And so getting this number here doesn't do anything for me. I've got all these differences, but I don't want to add them. So what we have to do is we actually have to square them. So in order to be able to use them, but that sort of messes things up, because when I square them, I then know that the standard deviation is, you know, 6.2 smiles squared, and there isn't really a thing called smiles squared that's not really an actual number, so you then have to take the square root. So if I take 0.4 times 0.4, I get 0.16. Alright, remember this was my x, here's my x minus x bar, and this is my x minus, this is my x minus x bar squared. Alright, if I take 3.4 times 3.4, you get 11.56. 5.4 times 5.4 is equal to 29.16. 3.6 times 3.6 is equal to 12.96. And 5.6, or negative 5.6 times negative 5.6 is equal to 31.36. Okay, now you can actually sum up these columns, all right? So if you double check, make sure that equals 0. I've got 31.36 plus 12.96 plus 29.16 plus 11.56 plus 0.16, right? Gives me the 85.2. Alright, so my sum of x minus x bar squared is 85.2. I can then take that, and what the formula tells me is that my standard deviation is equal to the square root of 85.2 divided by n, which is 5. Alright, 85.2 divided by 5 is equal to 17.04. Take the square root of that. Is equal to 4.12. Alright? And so my s is equal to 4.12, or I could say that my s squared is just equal to 17.04. I don't know if all of you can see that. All right, I think a lot of you are getting stuck right there. Is equal to the 17.04. All All right, you do all of this again. This is just for the males. So what I've been able to garnish is I've got a mean of 7.6 and a variance of 17.04. All right, if I did everything again on the female side, I would end up with, let me put those numbers up here. Erase all this, and you can back it up if you want to. What I end up with basically is I've got an X bar for males equal to 7.6. The standard deviation for males is equal to 17.04. And then I have the same information for females, right? I've got an X bar female equal to 15.2. And standard deviation of female equal to 8.96. Okay, I'm going to go ahead and I'm going to post all the work on paper, but the reason I'm not doing it right here is my videos seem to run too long and I can't find a place to upload them. All right, so I have those numbers, and then what I'm going to calculate now is the standard error of difference of the means, and this is straight out of your book, okay? And matter of fact, it is on page, let's see if I can tell you the exact page that the formula is on. I'm going to use the one testing the difference on page 167, 168. So if I use the formula off 168, I'm trying to calculate S x of 1 minus x of 2, which again, this is called the standard error of the difference of the means. You literally have everything you need. I know N1 is equal to 5. N2 happens to be equal to 5 as well. All right. And if I drop everything in, I'm basically going to end up plugging it into the formula. All right. So the formula says first N1 times S1 squared. All right. My N1 is equal to 5. My S1 squared is basically this, the 17.04. I can put this here. My variance. So 5 times 17.04 plus 5 times, because that was N2, times S2 squared. All right, this is my S2 squared, right? 8.96 over all of that over N1 plus N2 minus 2. So my N1 is 5. My N2 is 5 minus 2. Then we take this term here, and we're going to multiply it by N1 plus N2 over N1 times N2. So my N1 and N2 are 5. So I have 5 plus 5 over 5 times 5. All of this under the big square root. And I know some of you are forgetting to like square root things. I think it's just easier if you write down everything step by step. All right, let me keep going. Hopefully I won't run out of room here. So I end up with the square root of 82.5 plus 44.8 divided by 5 plus 5 is 10 minus 2 is 8 times 10, 5 plus 5 is 10, over 5 times 5 is 25. This is just equal to the square root of 6.52. Once I take the square root of it, I'm just left with 2.55. 2.55, all right? All of that just to get the standard error of the means, because remember, I have two different x bars and standard deviations, and I want to know what's the difference between the two. So now to do a test of the means, I'm going to erase this, but I'm going to write it up on the next one. After I get all my numbers, the next thing I like to do is basically draw the picture out. And I'm going to go ahead and get rid of all of this stuff so I have more room to work with, all right? I'm going to keep my null hypothesis up there because that's what I'm concerned about. But the idea here is, and you should be very familiar with drawing these, you need to draw one of these on every single problem. All right, the standard distribution curve. All right, in the previous chapter it was a Z. This is actually a T distribution, and there's book talks about the nuances between it. But what you want to know is, basically, because we're talking about a standard deviation, we're basically going to do a t-test to find out what our t value is, or the difference between the two, to decide, you know, do women smile more than women? Do women smile more than men, or is it about the same? So in order to do this, the t-test, I now need to calculate my t. I think some of you are getting confused. You're going to have two T's. You're going to have the one that you get from the back, which is called your critical T, and this is where you need to use the degrees of freedom, and let me go ahead and do that. I know my degrees of freedom in a t-test is equal to N1 plus N2 minus 2, all right? So my degrees of freedom for this problem, and for each test it's going to be different. In the next chapter when we do ANOVAs, the degrees of freedom is completely different. I'm going to have 5 plus 5 minus 2. So my degrees of freedom is 8. All right, and then if it doesn't specify, always use a 95% confidence interval, which means that alpha is equal to 0.05. All right, and the way you get this is you basically go to the table C in the back of the book. Let me pull that up for you because I know some of you are still having problems reading the tables. And it's totally normal because if you don't know how to read it or see one done, all right, if I go to table C, and table C is on page 367. And this would probably be helpful if I had a better view of it. But you're going to go down to where degrees of freedom is equal to 8, and you're going to go across to alpha of 2.306. 2.306. Now, if you know from reading up the table here where it tells you the T's, when you get the number, because it's a two-tailed test, basically you're left, the two T's are, there's a positive and a negative one. So the first thing I always do on my problems is after I get my critical T, before I even do my obtained T, I mark off my rejection regions, all right? So I know that at positive 2.306 and at negative 2.306, and what this means is 2.306 standard deviations away from the mean. And notice the mean here is 0. It's not what it was before because this is a T distribution. This isn't real life. This is simply after I get the T score, because I'm going to take my scores and convert them so I can look on the T table and kind of determine how likely it is that this is true. All right? I scratch off, highlight whatever, my rejection regions. And then all I want to know is my obtained T in these rejection regions? All right? Because I know 95% of the area under here, because I'm looking at alpha is equal to 0.05, which means that this tail is only 0.025. This is just extra info. And this is 0.025. All right? And I just want to know the area, this area here. And this whole area is 95%. Right? I just want to know where does my obtained T fall in this category. So to compute a T score, there's the formula, and let me give you the page that I'm using here. In chapter 7, I'm going to use the formula. I would write it on the board, but I've got such a, on page 168, which is just, you take the difference between the means, right? And I have two means, right? So I'm going to take my 7.6 minus my 15.2 divided by my standard error of the means, which I just calculated out was 2.55. So I take 7.6 minus 15.2, I get 2.55, right? When I do the math here, this comes to 2.98, right? Negative 2.98, negative. I go back to my chart and I look for negative 2.98, which is right about here. And so clearly that is in the rejection region. So and what that means is I'm going to reject the null hypothesis. And the null hypothesis had simply said that between the two here, there was no correlation, meaning that men smile just as much as women. I'm rejecting the null. I'm not necessarily accepting the hypothesis. I'm just saying that this is definitely not true. So what we do is we say we reject the null. We don't say we accept the hypothesis. We say we reject the null. All right? So my findings are that at an alpha equal to 0.05, I reject the null. There is a relationship between the number of times someone smiles and whether they're a male or a female. All right? That's it.